We've got 4 presentations, 3 long papers and 1 short paper. Is the speaker for the short paper here? Okay, we do have all 4 presentations. All right, so we're going to start out with Session IVa, who's going to be talking about making hybrid plans more clear to human users.
Okay. So, recently planning technology has been applied to domains such as emergency planning, assistance of cognitively impaired and elderly people, and support daily activities. So in these domains, the planning system provides recommendations for when and how to act to human subjects who might be just more or less competent in these domains themselves. And this leads to the problem that a human user might question these recommendations. And if the system is not able to answer these questions, then mistrust in the system's competence could be provoked, and maybe even the plan will just be disregarded. So in our opinion, a planning system must have the ability to give reasons for the decisions it made and present them in a comprehensible manner to thereby build trust in the system's competence. So our contribution in this work is the specification of a framework for the generation of what we call raw plan explanations. So we can imagine that a raw explanation represents the content of an actual humanly readable explanation. So the raw explanation could be used as input to, say, a natural language generation system that then produces the actual readable explanation. So in this framework we have implemented the explanation for the existence of actions and order of actions. So we are now able to answer questions by the user such as, why do I have to execute this action A from the plan? Or why do I have to execute this action A before that action B? And based on this framework, we have implemented a prototype system that can generate such raw explanations. The basis for my explanation framework is a hybrid planning framework, which combines aspects from classical and hierarchical planning. In this framework, planning problem is simply triple. First, we have a set of tasks, which can be partitioned into sets of primitive and abstract task schemata. The primitive tasks simply take over the role of the operators from classical planning, and the abstract tasks represent high-level activities that are usually composed of several primitive tasks. Then we have a set of decomposition methods. These define predefined solutions for the abstract task in the form of small plans. So during planning, the abstract task will be solved by just replacing them with one of the plans from their respective methods. And finally, we have an initial partial plan that needs to be decomposed by the planning system in order to find a solution. And typically, we have 2 artificial plan steps, init and goal, where init has the initial state as effects and goal has the goals as preconditions. So a partial plan is a for tuple with sets of plan steps, ordering and variable constraints, and most importantly for us, a set of causal links. A plan step is simply a pair of a unique label and a partially instantiated task. The ordering constraints define a partial order on the plan steps to represent the order of execution. The variable constraints can be used to bind the variables from the partially instantiated task to other variables or constants. And finally, a causal link between plan steps S and S prime over precondition P of S prime represents the establishment of this precondition by the effects of S. Such a plan is a solution to a planning problem if every precondition of every plan step in the plan is established by one of these causal links. Second, none of these causal links are threatened. So that means between S and S prime, no plan step may be ordered that has P in the delete list. So these 2 conditions ensure that the plan is executable and reaches all the goals. And finally, the plan may only contain primitive tasks, and it must be able to obtain it from the initial plan by decomposing the abstract plan steps and by inserting plan steps, causal links, ordering and variable constraints as we like. So most important for this talk is we have causal links to represent the establishments of the preconditions, and we are decomposing abstract plan steps via these methods. Okay, this is my running example for this presentation. It is taken from a new domain which we call smartphone, and in this domain the planning system gives advice to the user of a smartphone on how to organize tasks from his daily life. So in this case, the goal of the plan is simply to send a photo from the smartphone to some other person in any way possible. So here, the plan works by first entering the photo album, then selecting a picture from the photo album, choosing the send by email function from a context menu, and so an email program will pop up, and in this program we choose a recipient and press send. Then we have, so these are basically the primitive plan steps. And between the plan steps we have causal links depicted as these arrows, and they are annotated with the name of the precondition that is established by the causal link. So in this example, enter album establishes the precondition in album mode of select pick. Then this plan was constructed by decomposing two abstract plan steps for displaying the picture and then sending it. And these are connected to the plan steps that were inserted into the plan through their decomposition by these diamond-shaped arrows. And they are annotated with the name of the method. So the abstract plan step display pick was decomposed with the method display pick via album into these two plan steps. And finally, I use an artificial task called top, which simply decomposes into the initial plan of the original planning problem through this method mtop. This is just a little trick that allows me to formulate part of my explanation framework more elegantly later on. Okay. So, the basic framework for plan explanation. We use a first-order logic axiomatic system. And in this system, we formalize information about the plan, the construction process that led to the plan, and basic arguments for the explanation in the form of axioms. So in this framework, constructing an explanation means to find a proof for a first-order logic formula that represents the aspect of the plan that we want to explain. And since all elements of this axiomatic system are based on the problem specification, the underlying planning formalism, and the construction process that led to the plan, we can say that our explanations are correct with respect to the underlying planning system. The most basic elements of our axiomatic system represent the causal and decomposition structure of the plan. So the causal structure describes how in the plan preconditions of plan steps are established by the effects of other plan steps. And since this establishment of preconditions is in our planning formalism explicitly represented by these causal links, we get for every causal link between a plan step S and S prime over precondition P, one atom with corresponding arguments over this predicate symbol CR, which is simply short for causal relation. And so in the same manner, the decomposition structure describes how during planning abstract plan steps were decomposed into primitive plan steps. So for every plan step S that was introduced into the plan by the decomposition of an abstract plan step S prime through a method M, we insert an atom with corresponding arguments over this predicate symbol dr into our axiomatic system, where dr is short for decomposition relation. So I will give some examples. So this is a small excerpt from my running example. And so here we have, for example, a causal link between enter album and select pick over this precondition in album mode. So therefore we simply get an atom with enter album, album mode, and select pick as arguments over this predicate symbol CR. So this is very simple. And in this plan, send pick was decomposed with the method send pick by email into this plan step press send by email. So we get an atom over predicate symbol dr, which with these two plan steps and the precondition as arguments. And you can think of these atoms as the elementary building blocks for our explanations. And now I will formulate the rules by which we combine these building blocks to form an explanation. Okay, for this I introduce a new predicate symbol called nec, which is simply short for necessary. And nec of S should denote the information that the plan step S is necessary for this plan to be a solution. And I want to make clear that this does not mean that there cannot be a solution plan for the same planning problem which does not have S. It simply means that we cannot take S out of this plan without spoiling the correctness of this plan. For some reason this seems to confuse some people. Okay, so this means in my framework to construct an explanation for why the user has to execute plan step S, I have to construct a proof for this atom, and then I can take that proof and insert it to, say, a natural language generation system, and that will produce the actual readable explanation. Okay, so there are 4 ways to show that neg of S is valid in the axiomatic system. First, let's say there is a goal, and this goal is actually established by the effects of S. Then I can really say, okay, I cannot take S out as it is really necessary for this plan to be a solution. Second, I have a plan step S prime, and I have already shown that this is necessary. Then if S establishes one of the preconditions of S prime, I can also say, okay, I cannot take S out as it's really necessary. Then the second 2 axioms do the same for the decomposition relations. So if S is a substep of top, which means S is a plan step from the initial plan of the planning problem, then S must really be there because it was specified by the user that it has to be there. Specified by giving the original problem formulation. So this is actually why I use this plan step top, because it allows me to represent with a decomposition relation that the plan step was from the initial plan. So and finally, if I have a plan step S prime and I've already shown that this is necessary, then I can say a substep S of S prime must also be necessary. Okay, I will give an example. In my running example, I want to explain why this plan step anti-album is necessary. So I have to show that this atom is valid in my axiomatic system. And I have these 4 axioms available and the causal and decomposition relations from the plan. So now I have to decide which of these 4 axioms I want to use to show this. And usually I can use more than one of these, so there are usually many ways to explain a plan step. In this case, I will use the second one. So this one says, to show that anti-album is necessary, you have to find a causal relation between anti-album and some other plan step S prime, but then you have to show that S prime is necessary. So in this case, I use a causal relation between anti-album and select pick, but then I have to show that select pick is necessary. Okay, so how do I do this? I use, again, the second axiom. So I choose in this case this causal relation between select pick and present by email, but then I have to show that that one is necessary. Now I could use the second axiom again, but just for a matter of taste I choose the 4th one. So this just swaps the causal relation with the decomposition relation. I use the one between present by email and send pick. And finally, send pick is a substep of top, so I can use the 3rd axiom, which says if a plan step is a substep of top, it is necessary. Okay, so obviously nobody can really read this. So I will show you what we would imagine what this would look like if we transformed it to a natural language, which we cannot do as of now, but we hope to do it in the future. So you could read this as follows. Entering the album is necessary to select the picture. You must select the picture in order to use the present by email function. And that is a necessary substep of sending the picture, which is part of your own initial problem specification. Okay, so now we can construct some simple example explanations, but I'm not quite satisfied yet. If you explain something in real life, you can never give all the details. You always have to explain on a more abstract level, and you can just go into details every here and there, depending on what you find most important. And we want to be able to do the same thing in our explanations. And we have actually partially tackled this already by allowing the use of these decomposition relations. So these allow us to go to a more abstract level in the plan. But now we have a problem. As I mentioned before, the causal structure so far contains causal relations for each causal link in the plan. but depending on the underlying planning formalism, the planner does not have to add these causal links for the abstract plan steps. Only on the level of the primitive plan steps I can be sure that the causality will be completely specified in the plan. This means that in general I can only explain an abstract plan step through these decomposition relations. So that means once I have gone to the abstract level, I can only get to even more abstract levels, so I can never get back down to the primitive level of explaining the plan. And we want to solve this as follows. What we want to do is we want to calculate the causal relations for the abstract plan steps ourselves within the framework. So if the planner is not doing this for us, we just do it ourselves. So for example, let's say we have a causal relation between select pick and present by email over this precondition. Then, and also we can see that select pick is a substep of display pick. Well, then we might just as well say in explanation that display pick establishes this precondition pick selected for present by email. Or the other way around, we could say that select pick establishes this precondition pick selected for send pick. So in this way, we let the abstract plan steps inherit the causal relations from their substeps. And then we could use these inherited causal relations just like any other causal relation in an explanation. And this is actually captured by these two axioms. So this first axiom says, if you have a plan step S double prime, in this case select pick, which is a substep of display pick, or S in this axiom, and you have a causal relation between S double prime and S prime, in this case select pick and present by email, you can actually derive a causal relation between S and S prime, so in this case display pick and present by email. And then the second axiom allows us to derive this causal relation, and of course we can let this causal relation be inherited again to even get a causal relation that is only between abstract plan steps. So now we can go back and forth between the levels of abstraction in the plan as we like. Okay. Okay. So I guess I have enough time to go a little bit over this. So now we can let abstract plan steps inherit these causal relations, but sometimes this will produce explanations that do not sound very reasonable. So for example, in my running example, I can derive these causal relations between send pick and the goal. So if I use these in an explanation, it would sound like this. You have to send this picture because you wanted to send some email. Or if I use the other one, I would say you have to send this picture because you wanted to attach this picture to some email. So using either of these explanations alone would not sound reasonable. It is actually the high-level goal that we wanted to transfer this picture to that other person that is achieved by these two goals in combination. And we would like to reflect this in our explanations. So what we can do is we introduce a set of decomposition axioms, and these define what you could call high-level state features. So in this case, we say that transferring a picture is equal to attaching that picture to an email and sending that email. Or, for example, to printing that picture and sending it by fax. And now we want to derive causal relations over such an abstract literal as this. And this is actually made possible by these two axioms. I guess I don't have enough time to explain them in detail. But using these, we could, for example, derive this causal relation. And if we use that in an explanation, it would sound like you have to send the picture because it was your goal to transfer this picture to that person, which sounds a little bit trivial, but is more reasonable than using either of these causal relations. Okay, we have implemented a prototype system that will generate explanations as specified by this framework. And the good news is, doing this seems to be computationally quite easy. So usually we can generate just thousands of explanations within a few seconds. So the question is not how to generate an explanation efficiently, it is how to select among these large abundance of explanations. So there are a few quality features that come to mind, such as the size of the explanation, type of argument used, the means we have available for presentation, so if we can display only text or graphics, or if we only want to give out some speech. And of course, it is important to know what knowledge the user has about this application domain. For example, to decide on what level of abstraction you want to explain what part of the plan. Okay, in summary, we believe that communication of plans is a crucial ability for the acceptance of planning technology in a wider range of applications. So here, as a first step, we have presented a general framework for the generation of explanations, and we have instantiated this framework for the explanation of plan steps and the ordering of plan steps within the plan. I didn't go into this in this talk, but it is in our paper. And we believe that future work should deal with first the presentation of these explanations and how to select a raw explanation from this large amount of explanations that we can generate. Thank you for your attention.
So it's time for some questions. Andre?
Is it also possible to use these ideas for finding optimal goals, for finding optimal plans, for example, on cost? You want to find actions that has to be the best plan for something?
I wouldn't think so, because it analyzes the plan that is already there. So I don't think so. At least I've never thought about it.
So one of the things that I've come up against in this type of thing is show people a plan and they want to know why this action isn't used. Mm-hmm. Right? They want to say, well, I would have used this action, but it doesn't appear in the plan. And so is there any extensions that you can see to actually start reasoning about why this action is not in the plan?
Okay. So the good thing about this type of reasoning we do is that it is quite efficiently possible. What you suggest would, I suppose, mean that you would have to just plan again, but say, don't use that action. And so this would be computationally much more difficult, I think. I know there has actually been work about explaining why we couldn't find a solution for a planning problem in a particular situation. So I think that would more fit into with that idea. But yeah, I think that would also be good to use such information in an explanation.
Yeah. Any other questions? Okay, thank you. Okay, so the second talk in this section is going to be given by Simon Parkinson. It's the application of automated planning to machine tool calibration.
Okay, my name is Simon Parkinson from the University of Huddersfield, and I'm going to describe our problem of machine tool calibration. So I'm going to start by giving an overview of what the problem is. So for those who don't know, a machine tool is a mechanically powered device which is used for machining components. So you have two examples, one on the bottom where we're manufacturing the skins of an aircraft wing, one on the top where we're making very small false teeth. I mean, machine tools are used for a massive variety of components, so I don't think you could go through your daily life without using something that's being machined. Now, machine tools have a working volume, and you need to establish the predictability of the machine throughout that working volume, because all machines have errors. So, and the demand to manufacture parts of a higher accuracy results in the requirement of machines that are more accurate, because you can only make artifacts that are as good or as good as the machine's accuracy. So making the machine more accurate, you can manufacture more accurate components. And I'd just like to show you this machine at the bottom here, which has a very large working volume for making these turbines that you can see on the right. But it has a volumetric accuracy of only 20 microns. Just put that into perspective, the average human error is 70 microns. You can see this machine is very accurate and highly predictable, but this machine costs well over £2 million to buy. So all machine tools have errors because they're made up themselves of manufactured parts, and when you manufacture something you make it to a tolerance, and these tolerances propagate through the machine and then you get the error. So you can see on this picture here you have the machine's expected position versus its actual position. So the process of calibration is the process of understanding all the different error components that come together to make this deviation. So performing a machine tool calibration is an expensive task. The machine needs to be taken out of service for quite a lengthy period. So you really need to make sure that you get it right first time. And on the bottom here we have a picture of a machine that has a 72-metre traversal length, and you have to measure all the geometric errors across that entire length. And that's going to take a long time. You've got a lot of measurements to do. The machine's going to be out of service for at least a week. You need to make sure that all the results you get are usable, otherwise you've wasted time. So expert knowledge is certainly required. You need somebody who's very experienced in this area to come up with a calibration plan. So just to summarise, calibration can be broken down into the following sub-processes. First of all, you'd analyse the machine's configuration to determine the geometric errors. Then you'd prioritise these, which ones are more important depending on the machine's configuration and what you're manufacturing. You'd select the best measurement method, and then you'd select the best equipment for that measurement. So first of all, we'll just look at the machine's geometric error. So a machine tool will often move in two-dimensional space, X, Y, and Z, and then you'll also have two rotary heads on the end of the tool. So it's kind of familiar to like the robot action that you'll all be familiar with, but instead of this you move normally a big table for stability reasons. So with a linear axis you have the standard 6 degrees of freedom, and you need to measure each one of these error components individually, and then from this you can establish the overall volumetric accuracy. And the order in which these axes are stacked on the machine determines the propagation of error. So if you have a linear axis then another one on top, the first axis, the error propagates through to the second one, so it's more important to measure this one first. So with measurement methods, there's a lot of different standards available, but we use the ISO 230. And in there, there's two methods here, just for an example, for measuring the straightness of a linear axis as you traverse. One of them uses, on the left, uses a reference edge and a dial test indicator, so as you move you can see the deviation. Where the one on the right uses laser interferometry, which is good for long travel, where you'd use a straight edge for very small machines. So with the measurement methods, a lot of the instrumentation you can measure different error components. Like here we have two pictures where we're using laser interferometry. The one on the left we're measuring positional deviation, the one on the right we're measuring vertical straightness. So once you've got the laser aligned parallel with the axis, and then you've got the optics aligned with the laser, it's often easier to change the optics over to measure a different error component rather than getting some new instrumentation and start again. So you can save a lot of time by optimizing the sequence of measurements depending on what instruments you're using. So with some of the measurements, you can measure more than one error component at one time. So say if you're measuring the horizontal straightness of an axis, you might also be able to measure the linear positioning if you can get two instruments on there at once. But this depends on if there are any physical limitations of the machine and its environment, if there's any instrumentation interference, and if the measurement parameters themselves are compatible, so the speed at which you traverse and the number of samples you take. So we thought it was a good idea to use automated planning to try to produce the optimal sequence of calibration tasks, so we could reduce machine downtime. First of all, we started out with a hierarchical task network with the shop 2 architecture, because we thought the way that machine tool calibration could be brought down into smaller subtasks would be an ideal solution. And then we moved on to a PDDL model with the LPGTD, which I'll explain why in a minute. So with the HTN, we have an abstraction here where you can see how we broke it down. This is very abstract, but just to show that it could be nicely represented as subtasks. But then we moved to the PDDL encoding because it's easier in PDDL to represent time and concurrency. So in our PDL model, and also you can use a larger variety of planning algorithms. So in our PDL model we use quantification numbers, time initial literals, and also derivative actions, obviously because we're trying to optimize in terms of time. So time is very important. So in our model we have several temporal constraints, so I'll just go through a few of them here. So if we're planning to do multiple measurements on one axis, you need to make sure that all the instruments that are set up on the axis have to be on the same axis for more measurements. And each instrument will have a maximum number of tests that it can perform simultaneously, so how many degrees of freedom it can measure. And on some axes it's not possible to use certain equipment simultaneously because of instrument interference, so you wouldn't have like two lasers because the beams might cross and it just wouldn't work. And then also testing can happen over a number of days, but we need to schedule it into an 8-hour period because you wouldn't want to get to the end of a day and have a measurement set up but not finished, because it's not good for measurement traceability. You need to optimize the sequence. So also we have some spatial constraints on the machine's design and location, which can prevent the use of some instrumentation. You might go to an industry where the machine is in such an awkward position and you just can't set up your instrumentation outside of it to get the laser in, or the machine's volume might be so small that you just physically can't get in there, so you have to be very careful of what you use. And also the operating range of the instrument must be greater than the desired traversal length. So in our model we have three types of error. Objects, so we have the axis, instrument and error. And these two diagrams here just give an abstraction of how our operators are manipulating the objects. So you can see with the instrument, it can set up to measure an error, but then it can also adjust to measure another error. And it can be removed for a new instrument to come in. And with the error object, it's either set up, adjust or measure. So in our model, we have two plan metrics. First of all, time. We want to minimise the total time of the calibration. But also, if you don't have enough time to perform a full calibration, you want to optimise in terms of what you're measuring. So we assign an importance value to an error component from the way that they propagate through the machine's kinematic chain. And then if the time's not available, we select the most important ones first, so that you can calibrate the most significant errors to try and improve the accuracy this way, and then you can come back later on and measure the ones that are not as important. And to do this, we take into consideration what the machine's actually being used for. So if it's a really large volume, but you're only using a certain part of that volume, we'll concentrate on measuring there rather than the other parts. So we take into consideration the customer's requirements. So in our initial state, we have all the setup and adjustment times for the instrumentation, which instrumentation can measure which error, and all the errors that need to be measured, and the importance of each axis and error. So then in our goal state, we can either pose all the error components that we want to be measured, or if we don't have enough time, then we pose an empty goal and leave the planner to try and select the best ones, the most important errors to be measured. So here's just a comparison of our two models at the top there, between the SHOT 2 and the LP GTD, and you can see that there's very little difference. But the one beneath is when we enabled concurrent measurements, so that multiple measurements can happen simultaneously. And you can see that this significantly reduces the time. And this is interesting because a lot of engineers who calibrate machines don't really think of performing measurements simultaneously. They like to do it sequential. So when we produce some of these plans, they were quite surprised that we can optimize in this way, and they found it quite beneficial. So I thought I'd just go through a case study with one of our industrial partners of a 5-axis gantry machine, which has a total of 41 geometric error components. And we have two expert plans, one from an academic and one from the industrial partner. And then we have the HTM produced plan and the PDDL produced plan. So So both of the academic plans, the expert plans, sorry, differ significantly because of the motivation. So the academic is just interested in measuring them all and then taking the data to analyse, whereas the industrial engineer is interested in measuring the errors in the way they propagate through the machine, so that if they find a significant error, they can compensate for it, fix the error, then move on to the one after it. Because if you was to measure them in the wrong order, you would end up compensating for an error after you've measured another error which could interact, so you'd end up with false results. So the times are not so different, 1 hour difference, but when you consider machine tool downtime, 1 hour is a large sum. So for the industrial partner that has this machine, 1 hour downtime for them is well over £10,000 because of the knock-on effect it has on their production line. So here we have might not be too clear to see it, here we have the industrial and academic plans, and you can just see the sequence of events and the error component. You can see how it's how the plant completely different. So in our model we have to take into consideration that some people just want to measure all the errors for optimal time, whereas some people want to measure them in terms of which error is most important, and that's why we have the two plan metrics. So with the HTN plan, we produced a very sequential plan, and you can see that it's optimized here in terms of setting up the equipment and then readjusting it for another error component before moving on to another axis and performing the same. Whereas with the PDDL plan, where we enabled concurrency, you can see that in some places like here, you're able to set up two different instruments to measure two different error components at the same time. And this is what the industrial partners really liked, because this saved them a lot of time. So here's the results overall. So the PDDL plan with sequential measurements saved just over another hour of the plan, which is another £10,000 really. So even though it doesn't look so significant, it is. They saved a lot of money from this, and they tried our plan out and actually followed it through to test the validity of it, and everything seemed to be okay. They did find out some other restrictions that we need to include in our model, but everything seems to be reasonable. So in summary, I'd just like to say that we've modelled the process of calibration, machine tool calibration, in PDDL and HTN. And we believe that the PDDL model that we've got is much better than our earlier HTN. We can optimise both in terms of reducing machine downtime and finding the most important errors and measuring them first. But for the future, we need to consider more errors about the machine, because we're only looking at geometric error at the moment, but there's many more error components to consider, such as dynamic errors, thermal errors, and we need to include all these. And since we submitted this paper, we've been doing work expanding this model to other measurement problems. We work with one company who's very interested in applying this to the measurement of complex geometries of different artifacts, and finding the most optimal solution to measure these. They want to do it to maximise or minimise measurement uncertainty and measurement traceability. That takes me to the end. So, thank you.
So we have plenty of time for questions.
Have the plans you have produced been validated by the experts on the system?
That's right.
Did they raise objections with any?
Some of the early ones did it, yeah. We've had to prove the model, we had to add more constraints, if you like. But overall, they seem quite happy with it.
Okay.
But we are, in our model, we take a lot of consideration as to the machine's configuration, the environment. So it's a very heavy problem, if you like. There's lots of it.
Other questions?
Yeah, Simon, I mean, it saved a lot, maybe potentially saved a lot of machine cost.
Yeah.
But what about the cost of encoding the model?
Yeah, this is where we need to go in the future. Yeah, we need an interface, because we can't have people write on PDL. and code it all the time.
So you need a good knowledge engineering
Yeah,
tool.
definitely.
Any questions? So I have a question. So since I'm a scheduling person, I want to solve the problem of scheduling. And one of the things I could see doing is basically figuring out all the possible activities, measurement activities we can do. Some of them I can choose not to do.
Yep.
And so if there is a ginormous number of those, then obviously what you want to do is the planning where you can actually choose which one of these and do the instantiations.
Yep.
But if it's feasible to actually say this is a set of activities and choose which ones to do in which order, then scheduling might be more appropriate. So can you comment on that in terms of the scaling of your case studies and where you want to go?
Oh, maybe you're right. I've not really considered that. It's not really looked down the schedule in mind, but the scalability. There's so many different machine configurations out there. And finding all possible measurements is quite computationally expensive. But maybe I'll keep that in the future.
So you think there's enough different parameters within the different measurements, within the different actions,
Yeah.
operators, that you really do need a planning
Yeah.
framework to do this? Other questions? Okay, thank you. So you've got a whole lot of time. All right, so the third talk in this session is going to be presented by Antonio Garrido, and it's using AI planning to enhance the e-learning process.
Thank you for coming. The first thing that I want to say is that this is a joint work with Lluvia Morales from Mexico and Ivan Serena from Italy. So the idea of this talk and the outline is something like this. First, I'll speak about the problem definition, the motivation, why to use planning. Then we'll present our approach that is called my PQ talk, and we are not very sure about what P stands for. We say planning, we say personal, so it's not very clear. We'll see the architecture and we'll see all the stages. How to define the course, how to compile into a PDDL model, how to solve the problem, how to run into a learning management system, and so on. Then I'll present how to integrate with a learning management system as Moodle. And finally, we'll see some experimental results and the conclusions. Okay, something about the definition of the problem. Now, education, mainly in the university and particularly in Europe, is changing a lot. The student is playing a very active, more autonomous role in which they don't go to the seminar. They are there, and what they need to do is just to work and to study, to analyze, to do many more things. So in that case, e-learning and e-teaching, everything related to electronic is getting more and more important for that. Also, if we're speaking about the internet, the web is full of learning resources. What is a learning resource or a learning object? Everything. I mean, we can say that a learning object can be attending a seminar, reading a book, watching a video, anything that we can think it can be a learning object. But the main problem about this is what experts in education say is that it is highly dependent on the profile of the student. For instance, if we have a student that is visual, I mean this is the learning style that the student has, it's better to have something like a video. For other students, it's better to attend to a seminar. So it's important to choose the right learning object for the right person. It's not just this learning object for that person and that one for a different person. No. It's important to fit the style of the student with the style of the learning object. So that's essential. Right selection and combination of learning objects according to the profile of the student. So our goal for this work is to focus on the student-centered plan or learning route. In that case, what we want is to have something that is perfect according to the needs of the student. And after having the plan, we also need to execute that plan. It's not just a matter of having the plan, but also to execute, to run the plan, to use a particular navigator and to see that everything what is expected is happening as it should be. Well, planning. This is a conference about planning, so it's important to say why to use planning in here. Well, what we can see is that e-learning in many cases resembles with planning. In that case, we have the column for e-learning, we have the column here for e-planning, and what we have is that first, we have the background of the student and also the preferences. I am very good in this language, I'm not very good in that language, I have a background on science or whatever. This, talking about planning, can be the initial step. Something similar happens with the learning goals. I want to know something or a lot about planning or artificial intelligence or biology or whatever. That is going to be the top level goals in planning. In e-learning, what we have is learning objects that are very profile adapted according to the learning style of the student. In planning, this means having the actions with the preconditions and the effects. Again, what we have here is ordering relations. First do this, then do that. In planning, what we have is the causal link relation, the typical one. Also in e-learning, what we have in the end is the learning route. This is the plan for the planning, typical planning, with the sequence of all the activities, actions, or learning objects. And finally, what we have is what the teacher does. By hand or using decision-making techniques, the teacher can decide to put this learning object before that one, or just to change the number of learning objects according to many different things. In that case, what we have here is one technique for planning, in that case case-based planning, to be able to store, to memorize, and to store in a database a huge number of plans. After that, if there are new students, we can go to that database and try to extract the best learning objects or the best plan for those students. So our approach is something like this. Important to say that this is a kind of mixed initiative approach in which we have the teachers and also the students. The teacher for designing the course, also for validating the course, and the students for planning, for running the course. They enroll on that course and they want to see all the learning objects. The steps are something like this. First, what we have here is a kind of cloud. A cloud with all the learning objects. We can create new learning objects, we can go to the database that is called Internet and take the learning object that we want, and we can create, in that case, using one tool that we have implemented, we can create a course. With that course, what we do is to compile automatically a PDDA domain file with the information of the students, in particular the e-portfolio. We have the background, we have the learning style, we have the goals, and we create the problem file. So now that we have the domain and the problem in PDDL format, we can use a plan. Here we can use any kind of planning that supports PDDL, because this is standard PDDL. After that, we can store the plan in a case base. If the teacher says that that's good, otherwise the teacher can change something. And then what we do is to use a learning management system to play that course. We have again the students are playing the learning objects, are using the learning objects, and we do a kind of monitoring and checking progress. If everything goes okay, no problem, that's fine. If there is any kind of problem, I mean something that is not happening as expected, we go back to planning, pre-planning, or actually adapting the plan to the new scenario, and we are again in the same loop, in the same cycle. This is the tool that we have implemented. It's a graphical one that is some kind of planning oriented, because we have information about the requirements, the preconditions, the outcomes, the effects. We have also some information about the profiles of the students. We can say that this learning object is good for this profile, and it's been also extended with some other additional information. We have conjunctive, disjunctive, recommendation for preconditions, the same for profiles, and we are able to extend with more information about the metric, the cost of the resources that they are going to use. There are many things there. And with that tool, what we can do is to create a compilation of the of the domain. The compilation of the domain is based on the extraction of the learning object metadata. In that case, the learning object has some kind of metadata standard that says, I require this, I have this as an effect, and what we do, what the tool does, is to extract that information and to create the domain. For each operator in PDDL, or better, for each learning object, we have an operator in PDDL. In that case, we have the learning object name or the identifier. This is the name of the action. We have the same for the parameters. In that case, we have just one parameter, the student. We have also the duration, starting from the learning object metadata. Of course, if we are not dealing with temporal planning, this line is ignored, nothing about that. Then we have the preconditions. We have the information about the requirements. We have the information about the profile dependent information. And finally, we have the effects. Of course, the effects can be something like add on the learning object, or perhaps something related to the use of the resources, or having a reward, or something, any other metric that we want to define. And as a second point, what we do is to create the PDDL problem. The PDDL problem is taken from the e-portfolio of the learning management system, with the profile, the background, and the goals that the student wants to attain. After that, we use a planner. We can use any PDDL plan, because this is plain standard PDDL plan. But we thought, after we'll see that in the results, that using some case-based planning is better than using other type of planners. Because what we have here is a plan library, where we have here a huge number of plans, in which we can go to extract and to take some plans for working with other students. It's important to have a huge number of plans in order to be able to find the plan that is more similar. And more similar means that has more elements in common in the initial state and in the goals, trying to extract some information and to reuse in the new plan. Also, what we are doing is to merge or to use plan merging techniques. The idea is to decompose the plan in different lines, one per goal, and then trying to put all together in a higher or in a more complete plan. Also, this can be used for being the starting point for local search, and everything's being on top of our plan. After solving the problem, what we have is a plan. In that case, the teacher can decide to validate, to say whether he or she agrees or not with that plan. Perhaps some lines can be changed. I mean, this learning object must be before that one, because I am the teacher, I am the professor, I have a lot of experience, and I think that this is going to be better for this type of the student. So if the teacher decides to do these changes, that's okay. Otherwise, they are like the planner decides. And this is also important for learning route stability. That kind of stability is a measure for the inertia of the plan. It's important that if we are students, what we want is that when we start with a plan, if there is some kind of problem, we'd like to continue with that plan as much as possible. We don't want to restart with a new different plan. So that's important for us, to have that kind of stability, that kind of keeping as many learning objects as possible. Some of them are not okay because the scenario has changed, but the others should remain as much as possible. And what we've done in this case is to use Moodle as our learning management system. In that case, when we are using this kind of system, we are playing the learning objects. And this means to running all the learning objects and to be able to monitor them. In that case, during the execution, there are two situations that can happen. The first one is that the evaluation of an activity didn't happen as expected. For instance, if we are doing an evaluation activity, we expect the student to pass that activity. But in some cases, the student doesn't pass the activity, so that means that the remaining part of the plan is not longer executable, is not longer valid. The second possibility is that the profile of the student changes. For instance, at the beginning I had one kind of results, and in the middle of the part of the plan I don't have that result. So that means that perhaps some of the remaining learning objects are not valid anymore. What we do here is to create a new planning scenario to fit the new circumstances, to fit the new problem. We have here what initial state, and now is the current state, the current real state. The learning goals remain the same, although they could be different. I mean, this is also possible, but we haven't implemented that yet, but we think that this is a very simple extension. We are keeping the same learning goals, but they could be also different. And what we do in that case is to use a validator. Actually, we are using the typical validator for PDPL with the domain, the new planning problem, and the remaining part of the plan. If the validator says that, don't worry, no problem, the remaining part of the plan can be, or is still valid, everything is fine. Otherwise, what we need to do is to invoke again a planner, in our case the case-based planning, to solve the problem, or to solve the new planning problem that has been generated. And this, in our case, is called adaptation. What we are doing is to adapt the plan, because we don't want to create a new plan from scratch, but what we want is just to do some very small changes, some modifications, in order to have the new plan. Our idea again is to keep stability. We don't want to have a brand new plan. We use in that case LPG Adapt, that is a local search-based planner that incrementally modifies the plan candidate, taking from the information that was stored in the database. But also, we can use different adaptation systems, because again, this is everything encoded as PDDL, so we can use the type of system that we want. In our case, we think that case-based planning is very good because it can be used for evaluation, just to check whether there are some failures or not, that everything is working fine or we need to do some modifications, and also to prepare. Because if we discover one problem, one type of failure, what we do is trying to modify, to remove the learning object, trying to go to the database and to check other possibilities to solve the problem. The integration, how to put all together in a real tool. In that case, we are working with Moodle, but we could use a different tool. Moodle is very useful and is very common in many of the universities, not only in Europe, but all over the world. And what we've done is to implement some forms that are here. They are not very nice, but we are not experts in design. We are more focusing at this moment in the functionality for the teachers to decide, okay, this is going to be in the course, and also for the students to say, okay, I'm interested in that kind of learning goal, I'm also interested in that one, but I'm not interested in this one because it's not according to my profile or whatever. And what we do is to generate the plan. Also, we offer the possibility to export the information as a Gantt diagram. In that case, that uses Microsoft Project, and we have all the information there. We have all the learning objects, all the activities, we have the relations, and we have the result of the plan. Now, about the evaluation, what we've done is to have two different points of view. The first one is from a qualitative point of view, and this is a bit more difficult than the quantitative point of view. The problem here is that what we need is real teachers that want to work with this. And teachers don't usually like changes. They prefer to continue working in the same way, so when we say that, okay, we're going to use an artificial intelligence planner, they say, no, I want to be the human planner. So that's getting a bit of difficulties for doing this. But in general, what we can say from our small experiments, short experiments. We are still working in this. This is part of our ongoing work. Is that they agree with the form, the size, and the adaptation. But in some cases, they prefer to choose a different order, because according to their experience, they think that this is better or this is worse because of this particular reason. The good thing, the strong point of this is that they can change and update the database. From the quantitative point of view, it's important how to measure how effective is our approach. In that case, we are comparing this approach with emerging techniques with plan generation with other planners that are common in the planning community. We have experiments with 100 problems with different configurations that are changing according to the number of resources, according to the evaluation activities. This is artificial information that has been generated automatically. And what we have here is this kind of evaluation. First, we are comparing with other planners, SG plan and LPG, and in that case, what we can see in the results, in the blue and in the purple, in the red and in the green plot, is that the result is more or less okay, it's quite good. In terms of time, it's not as fast, for instance, as SG plan, but it's good according to stability, and this is something important that we want to remain in our domain, in our e-learning environment. Also, we've done some experiments here to check, using our planner, how important is to have a good database or not. How important is to have many more plans stored there in order to learn or in order to extract better results for the new students. It's important to say that in this case, what we've done is to work with an incremental case-based library. Rather than having all the results created by a different planner, what we do is learning from the new results that are generated after using one of the planners. The main consequence here is that this, of course, taking or working with incremental case-based planning and starting in that database takes time, that's for sure. But again, the good result is that the stability result is good. So in that case, we are paying something for having a longer execution, but that's better in terms of the stability, the quality of the plan. Don't want to know about PDDL. I mean, they're not interested in that. They want to use simple applications. They want to use drag and drop applications. And they're not really interested in how this is modeled, if this is curative actions. No. So everything must be done in a transparent way. It's also good to have some metadata extraction process. I mean, it's important, actually it's essential to have learning objects with that kind of information. Because if we don't have that kind of information, it's impossible to generate or to extract knowledge to create the course. Now in the internet we have a lot of things, but there are many things that they are useless from our point of view because they are not well labeled, and in that case we can extract any kind of knowledge. So that's important, and the good thing also is that we create a PDDL model, and this is valid for any type of planner. Also, although we can use any type of planner, we have compared and we have checked that using a case-based planning is better for the results according to the interest of the teacher, where some information is updated into the database and then is recovered from the database and everything is in the order that the teacher decides. And also is good for the students because the students think that, okay, this plan is for me and just for me. My colleague has a different plan, so that's good for promote the interest of the students. And that's all. Thank you very much for your attention.
Questions?
Among the main features of the system you mentioned, the fact that the plan is continuously monitored and readapted in case of the students don't let's say, comply with the initial plan which was created. And you also mentioned the aspect about the mixed initiative. Is the system able to recognize also possible mistakes from the teacher in case the teacher changes the plan? And if the teacher changes the plan, I don't know, some deadline could not be met for some reasons. Is this mixed initiative can build this inside the monitoring process?
It could be, but now at this moment we haven't implemented that. What we have is that we have the information about the plan, and the plan is okay according to all the relations. After that, the plan the teacher can make any kind of problem. It changes the order. If this goes against the definition of the domain, this is a problem. But we say, okay, the teacher
knows what
is the teacher, and okay, we agree with the teacher. But you are right, and we haven't implemented that. But that's something that can happen, and it's part of our work just to say at least to recommend the teacher that be aware that this doesn't fit what you said according to the domain.
Exactly.
I don't know if we need to keep the information that you say now or the information that you say in the past. But yeah, that's something that now the teacher has the last word.
Have you considered using a probabilistic framework to model things like student failure so that you don't have to replan?
No. This is, we have a plan in which we think that the student is going to pass. We don't have any kind, because we also thought at the beginning of having any kind of conditional planning to say, okay, this branch, whether if the student passes the evaluation, this other branch, if the student doesn't pass the evaluation, but it was very expensive. And what we thought is, okay, we are going to think that the student is going to pass. If the student doesn't pass, we'll check in that moment. So nothing about probabilities now.
Questions?
When you execute the plan and when you find some discrepancy, why don't you make any change in the domain file? I mean, for example, it could be possible that something is wrong while something that you described in the domain file. I said the system that you are using to teach the student, there might be some problems there, but it looks like that you are only changing the student profile, right?
There might be some problems in the domain, but for us the domain is something that you can't touch the domain, because we consider that the domain is good as it was. Perhaps that's true. Perhaps there is a problem in the domain, and what it's important or what is new should be modified or should modify the original domain. But we consider that the domain is something that we must follow. If there is a problem, there is a problem with the execution of the plan, not with the domain. But that's true. This could be also a possibility. But we don't consider that. The domain is something that is a kind of static information, and we can change that. Because if there is a problem, in that case, we need to go again to the teacher or to the course designer to say, there is a problem here with that student or with that profile. Is that really a problem with the student, with the execution, or is that a problem with the domain definition? And the last word in that case, again, is for the person, I mean, for the teacher or for the course designer.
A couple of questions. So one is, let's see, the system seems to be designed from the point of view of the teacher, but now there is a lot of, and I'm a user of these systems out there. There is Udacity and Coursera, these companies that put out systems. So now from the point of view of the student, many times I like to just start taking classes and areas that are of interest to me, but I may not be agreeing with all the prerequisites that a teacher may have said and so on. And I don't care in many cases, but I like to know what my goals are. So could the system support a kind of operation where the student is creating his own path, but the system is telling him where the goals are that he needs to fill? Now the other related question is, now there is all this data out there. Instead of having the teacher create it, would your system, what would it take for your system to ingest all this information that is out there and see the plans from outside instead of having to wait for a teacher to create it for you?
For the first question, okay, again, the student can choose when the plan allows the student to choose something. For instance, there are some learning objects that are not really sorted. I mean, there are not any ordering. In that case, we can say, okay, for the student, you can choose between 2 or among any number of learning objects, but only if these orderings are according to the information that is in the plan. And this for the first question. And for the second, I'm not pretty sure if I understood you correctly, because that information is stored about the plans in the database, and the teacher can modify that information. Because that information is modified, is again updated in the database, when the planning system is going to create a new problem, a new solution, that information is there.
So for instance, I took a machine learning class and there were, I think, 20,000 students, and they had a set of tests and so on. And so there is now a lot of information out there about what areas were particularly difficult for students. And when they fail something, what helped them overcome that obstacle and so on. So instead of waiting for teachers, somebody to create that, I think it would be useful to mine all that huge amount of information that is there now.
Yeah. Actually, what we have is the possibility for the teacher to validate or just to skip that validation in the case where the teacher has a lot of students. We think that the teacher is going to validate all the plans. This is our idea, but we have also the possibility to say, okay, I'm very busy right now, so I trust the planner, so I'm not going to validate anything, because according to the information of the planner, everything is okay because the domain was okay. But what we think is that the teacher should validate all the plans, but it's possible not to do that, and to have the information given by the planner.
So I work in engineering faculty, and we are controlled by the government about what the program has to be, and it's fairly complicated. Each course has so many units of engineering design, so many units of mathematics, and it's very difficult to give students options, because the minimal path through the network is what has to meet the regulations in terms of all of these different criteria. And so it would actually be very valuable to be able to have a much richer set of options and prove that the minimal path through this is actually going to meet the specifications from the government. So it would be interesting to sort of move that to a more numeric situation. I mean, it's a completely different situation. You're focused on students. This is focused on curriculum design. But I think some of the same ideas might map over.
Yeah, but I think that the options in that case can be not three and different options, but for instance, if I'm doing something about how to learn something about programming, I can do reading something, I can implement a piece of code, I can attend in a seminar, I can go to a talk.
Right.
These are the options. So in that case, if my profile is visual, because the experts say, or there is a survey that it says that this is my profile, this is the option. So it's not something that I'm going to do more learning object than you or not. It's that for the same result, I can use something different that is better for my profile. But in some cases, of course, when the government says that you need to do this, yes, we have a little component of planning there. I mean, this is what the government says. This is more thought to having a better opportunity to change and to choose this or to choose that. But if everything is fixed, no plan there. I mean, you have to do 1, 2, and 3, and in that order. And I don't mind if you are visual, if you are a verbal student, you need to do 1, 2, and 3.
Okay.
Okay. This is too limited for this approach.
Okay. Thank you. Who's the fourth speaker? Here's the last one. Yes, that's the last one. We have one more, so come on up. Come on up.
So I prefer using my own.
Yeah, that's fine. So it's a short paper, so it's 15 minutes plus 5.
Okay.
No, I can't be done in 15. So when I say 0, you still have 5 minutes.
That's fine.
Okay, so the final talk in our session is going to be given by Daniel Kerber. and it's on modeling the tactical planning and oil pipeline networks.
So, hello, my name is Daniel. I work at Petrobras, it's the Brazilian oil company. And I'm pleased to be here and talk about our modeling of the tactical planning of the oil pipeline networks. So at Petrobras, most of the transportations, most of the products are being transported over pipelines. And the pipelines are the preferred way as they have lower operational costs, they are safer to operate, and they scale well over large distances. This pipeline is shared by several commodities. That means that our model must be multi-commodity and also multi-period. That means we have a 2-month planning horizon, and this planning horizon is divided into independent time slices. Today, the topology of Petrobras, as being one of the largest companies, is quite complex. There are about 7,000 kilometers of pipelines, and for example, if you have a commodity at a harbor and it has to arrive at Brasilia, it takes about 2 to 3 weeks of transportation until it arrives there. And you have also to consider the lot of amount of commodities that are already inside the pipelines. That means if you start a plan, you have to consider what is already there. So our main goal is to assure minimal inventory levels at each commodity, at each facility. There are 4 important decisions to take. The first one is the amount that has to be transported. By choosing the amount, you give a priority to your transportation. That means that you won't be able to transport another commodity, for example. There's a time frame, as I've told, it may take 2 weeks until the destination, so you have to plan how much of the commodity will be on the pipeline before planning the next delivery. There's also the path. You saw there were multiple options of pipelines. You have to choose those ones that are not yet being used by another commodity. And there's the flow rate. There are pipelines going uphill, downhill, and different conditions. There is viscosity of the commodities. So each transportation has its own conditions. That we want a planning, and this planning has to describe how this flow will happen on the pipeline. We are still ignoring some operational scheduling issues. So this planning is not a schedule. The current solution that is used at the company is a classical network flow model. This model produces a solution, but it requires a lot of fixes done by the logistic analysts. So they have to use all the expertise and fix a solution, because the network flow model doesn't consider the flow rates correctly, it doesn't consider the inventory, it doesn't also consider the time it takes to the destination. That means the current solution is not yet a realistic description of the plan. And we see that there are 4 important aspects that have to be incorporated into our model. That is inventory of pipelines, that I will call as in-transit inventory, because they are commodities that are being moved over the time. It's the transit time, that is how long does it take to the destination. The flow capacity and the flow reversal. Flow reversal is especially important because if you are going to reverse the flow on the pipeline, it takes a lot of time, and this time has to be considered in your planning. That means you have to incorporate scheduling aspects into the plan. And there's a challenge. We know that linear programming is a well-known solution and also a proven solution for this problem. So that we know from literature that linear programming is a recommended solution. But in order to incorporate some scheduling aspects, we should use integer variables, but we do not want to use them, because without them we are able to provide a fast execution, and we will be able to handle large topologies. That means we want a linear programming model that is still suited for tactical planning. The topology is represented as a graph where each node is a facility. So you have production facilities, delivery and consumers. You have other facilities that may be consumers and producers at the same time. Or you have, for example, special nodes that are only transshipment. That means they take the commodity from one pipeline and forward them to the next one. And the pipelines are represented as arcs. There are some flow constraints. That means not all pipelines may deliver the commodities on each direction or each path. So we have an enumeration of paths that are the possible transportations that are able to be done. So for example, I have the red arrows that describe the possible transportations. We have a preprocessing that is quite good in enumerating this path without generating a large amount of data. And of course, as the pipeline is being shared by several commodities, we have to replicate the same model once for each commodity. So going to further details, we have a pipeline, an example. This pipeline is shared by two commodities. That means we have diesel and gasoline and a separator. I don't consider this separator yet. It prevents them from mixing with each other. And this pipeline has to be always completely filled. So if I want to deliver gasoline, I have to push more diesel into the pipeline so that it will be delivered at the other end. And it might happen that there is a third commodity that has to be moved backwards. So I have to push this green commodity and push out the previous diesel that was inside the pipeline. This may take a lot of time, and it has to be considered in the planning. Each node or each facility is described as a subnetwork with some decision variables. It is the inventory at the previous time slice for the inventory for the next time slice, and how much you produce and consume, and how much you are going to transport outbound, and how much you are going to transport inbound. This transportation is done over path. A path is a sequence of arcs, and for each arc, I have to decide how much is entering the path from the facility, how much will be delivered at the destination, and for each arc, I have to decide how much is being transported from each arc to the next one on the same path. And of course, each path and each arc has a commodity, an inventory. And you have to decide how much of the previous one will remain for the next one. So I have the same inventory model on each pipeline. And this model is extended for each commodity. That means several decisions on the same arc. And also, the same decision is taken for all paths that share the same arc. So it means a lot of decisions inside the arc. And you may note that this is the real behavior of the pipeline. We have several commodities there. But in my model, it's quite different. The commodities are all flowing at the same time. So in reality, my model is an approximation of the real model. And it doesn't consider the ordering of the commodities inside the pipeline. It doesn't yet consider the time it takes to deliver. Therefore, I have to enhance this model. And the enhancement is I expand each arc into a subnetwork. And for each arc, this subnetwork decides how much of the current inventory will be delivered at the destination, how much of the incoming commodity will be kept on the arc. That means I am simulating the behavior of the pipeline, so obeying these rules. This model alone doesn't yet assure this behavior. So I have to add some extra math on the objective function. That means if the correct behavior is kept by the model, then I get a solution with lower cost. So the objective function favors the correct behavior. Again, this is an approximation, so it is done over the objective function. And a step further, I have to assure that the time and speed of the commodities is correctly preserved in the pipelines. So how did I achieve that? I had to add additional constraints at the frontiers of each pipeline. That means everything that enters the pipeline must be equal to the total the amount that exits the pipeline. That means total inbound must be equal to the total outbound. That means that the capacity of the pipeline is always constant. And the next constraint says about the speed of the commodities. And at each frontier from one line to another one, I have to state that the time that is spent by the commodities inbound or outbound must be less than the time that's available for the time slice, for each time slice. That means if there's a slow commodity, then this slow commodity will take a lot of time to enter or to exit the pipeline, and this will prevent other commodities from entering or leaving the pipeline. And this slow commodity will prevent the entire path from flowing faster. Now, for example, about the benefits of this model, here's the classical flow network. I intend to transport 5 units of yellow commodity that is lightweight of low density. That means this commodity may flow fast. And I see that in only 70% of the usage of the available time, I am able to transport all this commodity to the second facility. But actually that isn't true, because I have previous knowledge that this pipeline was already filled with the green commodity. That is one of high density, and it has a slow flow rate, and therefore it takes a lot of time to first push out this commodity, and only then I may transport the yellow one. That means if I first push out 2 units of the slow one, of the green commodity, and then I am able to deliver the second one. And it takes 83%, not 70% of the available time. And also my model shows that isn't true, that I will get 10 units on this station. I will get only 8, because 2 of the units will remain on the pipeline. So there are two important issues. The amount delivered is necessarily equal to the amount that was pushed into the pipeline, and the time isn't as low as it was predicted by the classical model. Doing some experiments, we saw that for a typical instance with about 75 classes of commodities and 25 nodes or facilities and 45 arcs and a planning horizon of 2 months, if you divide these 2 months into 2 time slices, then it takes about 1 minute to execute. But if the time slice is growing number, and growing number means a better quality of the solution, then execution time increases. Actually, the solution is better than a manual solution, since the operator or the planning analyst has less work in fixing the solution. That means he doesn't need to care as much as before on the delivery time and inventory inside the pipeline and the flow rates. Our solution is more accurate than by the classical model. So the conclusion is we were able to include these 4 important aspects into the linear programming model. It provides a more accurate solution and better estimations of utilization rates. That means that our solution is closer to the reality. And more important, our challenge was achieved. We were able to provide a linear programming model for the pipeline transportation with no integer variables. So that's my presentation, and thank you.
Questions? Yeah?
So the integer model, what was the performance of the integer model?
We tried to avoid the integer model at all.
You didn't even have the
No. We did all work that was necessary to completely eliminate any integer elements from the model.
So the previous, before you did this, you had a model previously that needed a lot of fixing, right?
Yes, we had a pure linear programming model, but this model doesn't consider the important aspects of in-transit inventory and in-transit time and the dependency of the commodities on each other. So the logistic analyst, he generates his solution, but afterwards he had to fix a lot of issues because he knows that the commodity won't be instantly at the destination. It takes about 2 weeks. And he also knows that before doing his movements, he has to empty the pipelines. And all these issues weren't considered before.
Other questions? So you mentioned that you modeled the path variables. Every path is modeled as a variable in the model? Is that
Yes,
right?
really each path is a node, a kind of node that decides its own inventory and decides what you move onwards on how much you will receive.
And so how many paths are there in your network?
About 45, no, paths, no. I don't know by heart, I think it's about 500 paths.
So I mean, one of the standard things that people do for when they have paths that are essentially made up of a bunch of segments is you represent that as a variable, right? And you pre-compute those in your model. But
Yes.
sometimes when you scale up, because it's combinatoric in the number of segments, you end up having far too many path variables, right?
Yeah,
And
that's-
so I was wondering if a column generation model would be useful if you had to go larger.
Yeah, that's true. To avoid this problem, we have a heuristic that does enumeration as some rules, and we try to keep this enumeration with as few paths as possible. So, for example, we only have a path starting from a facility that has pumps to facilities that have tanks to receive the commodities. And if you mine the database, you also get which paths are not allowed because of constraints inside each facility. And the model really goes on the number of paths.
You tried 2 and 8 time slices. Did you try, 16 time slices or
Yes, that's an important question because we have observed that if you increase the number of time slices, there will be a number of time slices where the solution stops improving. And the cost of generating solution increases also. And we know for 2 months, 8 time slices is a good number, but we have to still study this more to get how this behaves. For example, I know that 1 time slice per day is a batch option. It generates a huge model that doesn't fit the memory of the computer, and it starts violating the relaxation. So for example, if you go back, as the commodities are flowing, as they were parallel at the same time, if the time slices are too small, the model doesn't correctly simulate this constraint. Yes. If the time slices are too small, this subnetwork stops working and the commodities start flowing directly to the destination. So I have to choose a correct number of time slices, and we're still studying what would be the best choice for that.
Last question?
What's the goal?
The goal is essentially to provide a safe level of inventory at each facility, especially at the consumer facilities, because there you have to have a spare inventory to provide enough commodities for the consumer.
Okay, thank you very much.
Thank you.
Can you put your slides on this? Because they're collecting the slides. So that's the end of the session. Have a good lunch, and remember we're coming back early from lunch for the plenary sessions in the large room, so don't miss those.